Hey guys, what's up? We are back in action here. Going to finish up our hypothesis testing discussion for sample means. And we are looking at today finishing up paired data. So this is the last thing in chapter 9. And we'll be done after we do chapter 9 today. We'll just stop and then we'll kind of take a break, come back Monday, do chapter 10. Wednesday, maybe do a little more chapter 10, maybe some chapter 12. Trying to slow down a little bit. I think next Friday we will not have class, if that's good with you guys. If you guys are okay with that. So just before we get started, I want to see if there are any questions. Probably like 3/4. Is it 3/4? I think about 5/6 of the way through with the exams. I have like 10 or 15. It's like 12. I think 12 exams left to grade overall. So I think everybody else's exams should be graded in your folder. If you want to check out your folder, you can see your exam graded in there. Now, I haven't analyzed the grades or anything like that. So I haven't decided like if that's your final grade or whatever yet on that exam, but I felt like a lot of people did pretty well overall. Two problems, number 3 and number 5, seem to be the one that people missed the most, as far as I can tell so far. Again, I haven't analyzed everything yet, so hard for me to really say what's going on with the grades yet. But for now, it's pretty good. So let's get to it. Let's finish up chapter 9 here and call it a day. And chapter 9. So far, we've been talking about two populations. Is test 3 a retest of 1 and 2? Yes. So curve possibly, Caitlin. Test 3 is a retest. Well, let me say the exam that's on Friday, the 15th of May, is a retest of 1 and 2. So yes, it is a retest of 1 and 2. All of chapter 1, 2, 3, 4, 5, and 7. Anything in there is fair game for that exam on May 15th. Now, the test on Monday, May 18th, is all the new material, chapter 8, 9, 10, and 12, which is really just a lot of confidence intervals and hypothesis testing. And then there's a little bit of linear regression stuff in there in chapter 12, but there's also hypothesis testing in chapter 12 too. So there's a lot going on in chapter 12. So we'll talk about it when we get there. We'll spend a good 2 days, I think, at least on chapter 12. So, and we'll spend probably about a day in chapter 10. So next week. So probably Monday. Yeah, probably Monday we'll do chapter 10. Maybe Wednesday, and then Friday we won't probably have class Friday. We'll see. And then chapter 12 the week after. So getting pretty close to the finish here. But yeah, it turns out senior grades are still due on Tuesday because you guys are still technically getting your diploma on the 23rd of May or something like that. Okay, nice. Yeah. So we'll see. We'll see what happens. I'm just playing it by ear right now. So, but that's kind of the plan for now. Anyway. Any questions? Other questions? Good stuff so far. Good questions. Sweet. Okay. Paired data. Paired data is a special case kind of this 2 sample stuff. And it's basically like a before and after. Like if you have before treatment and after treatment. It's the same person. It's just before treatment they had this value, and then after treatment they had this value. Or it could be like weight of husband versus weight of wives or something like that. Is there truly a difference between the people? You know, they eat pretty much the same stuff for the most part. They experience all the same things more or less. So is there a difference between, fundamentally, I guess, so those 2 populations? With paired data, we're going to have the N independently selected pairs. So these pairs are not like repeated in any way. Usually that's how it's independent, or that's how it's paired, in that they're independent. So you before and after a treatment is like independent of somebody else before and after a treatment. So, and the expected value of each population here is mu1 and mu2, and the difference is what we're going to focus on. That's our new random variable. So new random variable di is xi minus yi. So the expected value of mu, or of d, is mu1 minus mu2, because it's a linear combination again, I guess you could say. So the di's are one sample, so we do a one sample t-test. So basically we're taking a two sample question and turning it into a one sample question by taking the difference of the paired data. So what does this do? It takes two samples and turns them into one sample. So like xi and yi are the original samples, and then we take the difference, xi minus yi, and that creates a new sample, di. And that's a single sample now, because we're considering it to be paired. So our null hypothesis for a test would be that the mean of the difference has some particular value, and then our test statistic is calculated here. D bar is just the average of the differences, so the average of the differences. Di, so basically would add all those differences together and divide by the number of points, divided by the standard deviation of the differences, over square root of n. Okay, and depending on what alternative you have determines how you calculate the p-value. And it's the area to the right of the t value, or the area to the left of the t-value, depending on your alternative hypothesis here, or 2 times the area to the right of the absolute value of t. So we're using a t distribution for this paired data stuff. So we will do a one sample t-test. All right, so for example, so we have zinc concentration in the bottom versus the surface water, and we have 6 values. So n equals 6. It's our sample size. Well, actually we have 6 values at the top and 6 values at the bottom. So it's really 12 altogether, but we're trying to say, okay, we'll pair them up based on location. So I go to some location in my boat or whatever, and I take a surface reading with some surface water, and then I drop it way down and I get a bottom reading. I do that at each location in my boat. So I really have just 6 locations that I go to test the water. And I take a surface and the bottom reading at each location. And so we try to find out if there is truly a difference in bottom and surface by looking at the paired data. So now our single sample is down here in the red boxes that I'm going to put. So that's our D1, D1, D2, D3, 4, 5, 6. Okay, and you can add all those together and divide by 6, and you'll get this D bar right here. That's the average change, or the average difference from bottom minus top. So we're doing bottom minus top. And we calculate the sample standard deviation to be 0.0607. Don't forget, what's that sample standard deviation formula? It's like n equals, or I equals 1 to capital N of xi minus, or di, I should say, di minus d bar squared over n minus 1, take the square root. So that's how they calculate that S sub d, sample standard deviation, x, or di minus d bar squared. Just to make sure, di can be negative. Yes, absolutely. It's just a data point. It's just the difference of the two values. That's exactly right, Derek. It could be negative. It could be negative. But we're doing bottom minus surface here, so we get positive in each case. So now, if we're going to do a hypothesis test on this data, we could say that we think that the difference, the average difference, is 0. That'd be the null. No difference between bottom and top. The alternative would be that the difference is greater than 0, suggested by our data at least. In each case, the bottom was higher than the top, or the surface. So we're going to go with the alternative right here, that the difference is averaged larger than 0. So calculate our test statistic. We get 3.699 by using the formula. Round that to 3.7 so we can use our T-curve tails chart for T-curve tails. Degrees of freedom is sample size minus 1. And let's look up that p-value in our chart. So if we look up that p-value in our chart, okay, go to our T-curve tails. And we're looking for, we said 3.7 and 5 degrees of freedom. So let's go to our T-curve tails chart. And we're looking for 3.7, which is here. And we have 5 degrees of freedom, so we're going to this column. And there it is. There's our p-value, 0.01. P-value 0.01. So that's how they get that right there on the chart, right there. And it is less than the significance level, so yes, we can reject the null and say that the concentration of zinc in the bottom of the water is higher, statistically significantly higher than the concentration of zinc in the surface of the water. So the difference we see is statistically significant. Let's see. Oh, thank you. You're correct. Thank you. but yes, it's incorrect to say it's 0.01. It's actually 0. Is that 0.007? Yeah, 0.007. Which is even smaller, but you're right. It was wrong to say that it's this value here. Thank you. Okay, thank you. Thank you for double checking. That was good. Good catch. So the difference we see is statistically significant. So you can gather all this data, you can calculate all these statistics, you can make all these claims, but you have to know whether or not what you're saying is statistically significant. You see a difference. Is that difference statistically significant? Extremely important to know. So, we could do a confidence interval for the difference, and it's basically the same formula we would have for a single sample t confidence interval. We're using t because we have a small sample size. So, small sample size, we use t. Because we have s right here. We have to use a t distribution. All right, so any questions so far? Good questions. What if we were to do a 99% confidence interval for the previous example? So let's just throw in something extra here. Let's calculate a 99% confidence interval for the previous example, which means I need my t critical values table to pop up. There it is, t criticals. Okay, let me erase all this stuff we've used previously. Okay, what are we looking for? If we go back to our example, alpha here is 0.01, so alpha over 2 is 0.005. So we'll go to the 0.005 and the v equals 5 intersection. So 0.005 is this column. And we'll go down to the row 5. Whoops, go down to row 5 right here. And the intersection of those two is this value 4032. So 4.032 is our t value. So t sub 0.005 comma 5 is 4.032. So we'll take d bar, which was 0.0917. 0.0917 plus or minus 4.032 times the standard deviation over square root of 6. Standard deviation was 0.0607. And so our confidence interval for the difference is 0.0917 minus 4.032 times 0.0607 over square root of 6. So that's our lower bound. Negative 0.0082116, we'll say. And then the upper bound will be 0.191616. And that would be our 99% confidence interval. So that 99% confidence interval doesn't really suggest that there's a difference, but that's because we have such a high level of confidence. Basically, that's like alpha equals 0.005, and our p-value is 0.007. So this confidence interval doesn't really suggest anything statistically significant with our value. This says the difference may be anywhere from the top being higher by 0.008 to the bottom being higher by 0.19. So that's what the average distance or difference would be based on this confidence interval, this 99% confidence interval, but that's a really, really large level of confidence. So you have to keep all these things in mind when you're looking at the tests and the statistics and the level of significance and all that stuff. So cool. Last thing for this section is differences between population proportions. And this is huge when you're talking about things like elections. You have a certain number of people that you poll, and you want to get the proportion of people that are going to vote for somebody or something or whatever. So you get a proportion, and you want to know if the proportion is statistically significantly different. So not just is the percentage different, is it statistically significantly different? So the alternative, or the null hypothesis here, is that the proportions are the same. The alternative could be any one of these three. So 1, 2, or 3. And then we assume two sample estimates of the proportion that we calculate from the data, P1 hat and P2 hat, from the sample sizes M and N. Then the difference of population proportions is approximately normally distributed. So it's a normally distributed random variable. So the difference is normally distributed. With mean P1 minus P2 and standard deviation. So it's the mean, it's the standard deviation. So it's basically like P1 Q1 over M plus P2 Q2 over N. And that's the standard deviation. In case of a large sample size, your test statistic is right here. And p hat is this extra calculation thing that you have to do. So p hat is an extra calculation needed. Extra calculation needed. And that p hat thing is going to go right there and right here. And then we just use a z-test, which means you use a standard normal curve to calculate the p-value. So z-test means you use the z-table to get p-value. Whereas if it were a t-test, you'd have to use a t-table, t-curve tails, to get the p-value. So let's look at an example here. We have really large sample sizes. 549 and 730, so this is definitely going to be more than okay to use a z-test. Example, aspirin use after diagnosis of colorectal cancer. 549 participants in the study took aspirin and 81 died. 730 participants in the study did not take aspirin and 141 died. Is it statistically significant that 14% of the people who took aspirin died and 19% of the people who did not take aspirin died? So is that difference statistically significant? So there is a difference, but is it statistically significant? So is the difference statistically significant? So that's what we want to find out. Is this difference statistically significant? Sure, there's a difference, 5% roughly. Well, 4.5% roughly. So are the two percentages really different? Test at a level of significance 0.05 if aspirin indeed decreases the mortality rate in patients with colorectal cancer. Okay, let's calculate some things we need for our test statistic. First, we need that p hat term. So p hat, let's see, m is right here, n is right there. And p1 hat, we've already calculated. P2 hat, we've already calculated. So plug and chug, we get p hat is 0.1736. Now let's calculate the test statistic. So now the test statistic z is going to be, we'll plug and chug in that formula that we had, which was p1 minus p2, or p1 hat minus p2 hat over square root p hat times 1 minus p hat times 1 over m plus 1 over n. And that turns out to be 0.1475 minus 0.1932 over square root 0.1736 times 1 minus 0.1736 times 1 over 549 plus 1 over 730. And crunching that with your calculator, you should get negative 2.14. Okay. The null is P1 equals P2. The alternative, we'll say, is P1 less than P2. So our p-value is just going to be phi of negative 2.14. The area to the left, look that up in our z table. That turns out to be 0.0162, which is indeed less than 0.05, which is alpha. So reject H0. It is statistically significant that people who took aspirin had lower mortality rate . So yes, this difference is statistically significant. We can say that the difference is statistically significant. Questions? Last thing is confidence interval. And we have the formula right here for confidence interval for the population proportion, or the difference of population proportions. And because it's a large sample, so we're assuming large sample right here, we use a z critical. We use a z critical. So this is basically kind of going back to the binomial being approximated by normal if you have a large sample size, basically. So we will have a z critical that we use, and we just use the formula like we normally would for confidence interval. So this formula right here is extremely important. And let's look at chemotherapy versus chemotherapy and radiation in breast cancer 1997 study. And in this study, say this is M, this is N, 76 survived for 15 years out of 154 versus 98 survived 15 years if you had chemo plus radiation. So that means roughly 50% of the chemo-only patients survived 15 years or more, and about 60% of the chemo plus radiation survived 15 years. So is the increase that we see in chemo plus radiation treatment survival rate 15 years after, is that statistically significant? So is this 10% difference statistically significant? So is the increase in survivors 15 years after treatment statistically significant for chemo plus radiation? From this data. So we can only work with what we've got, and we've got this data, so we're going to test this data by creating a confidence interval. So we will create a confidence interval. So create a confidence interval. So we'll do a 99% confidence interval. Of course, in a real problem, you would be told some specific percentage to calculate, some specific percent confidence interval to calculate. But here I'll just do a 99% confidence interval. So alpha would be 0.01, and alpha over 2 would be 0.005. And so z sub 0.005, I need to look that up in the chart. Let's go to the tables, and we'll go to the z table and look for 0.995 in the chart. So 0.995 in the chart. Let's see, somewhere down here. .9950 is right in between these two. So 2.575 maybe. Try 2.575. Or just say 2.58. Why not? And then we use P1 hat minus P2 hat plus or minus 2.58 times square root P1 hat Q1 hat over M plus P2 hat Q2 hat over N. Let's see, we got P1 hat, P2 hat, so let's plug those in. This will give us a confidence level of, or a confidence interval of negative 0.247 all the way up to 0.039. So what does that mean? That means the difference is somewhere between negative 25%, so P1 minus P2, and 4%. So what does that mean? The difference between the proportions is greater than negative 25%, but less than 4%. Well, if the P2 was P1, basically, what could we say? Let me show you. Say P2 minus 25% equals P1. So that would say chemo only could be at most 25% fewer survivors. So it could be that chemo and radiation is like gives you 25% more survivors, basically, versus chemo only. However, it could be that P1 is less than P2 plus 4%. So it could be that chemo and radiation increases your risk of dying. So the chemo only may be 4% more survivors. So this confidence interval does not give us any clear indication that one is better than the other. So this confidence interval does not give a clear indication that chemo and radiation is better than just chemo. But we did a 99% confidence interval again, so that makes our interval pretty wide. And if you did a 95% confidence interval, then maybe, yeah, it would be more clear. Maybe they would both be in the negative. And then you could say, yeah, it could be as much as 25% better, or maybe only 4% better if it were negative 4 instead of positive 4. Anyway, that's the idea. We can do confidence intervals. We can do hypothesis testing. There's going to be all kinds of this stuff on the exam on the 19th, or the 18th, actually, the 18th. But yeah, that's it. I don't really want to go over this last slide. Don't worry about that. Just focus on these examples that we've done. Focus on the homework, book problems. Know when to use which test. Is it large sample? Is it small sample? Do I know sigma? Do I not know sigma? Should I use a z-test, t-test? What am I testing? What's my alternative? Which table do I use? T-curve tails, z-table. Next time we'll get a new table called the F distribution. So that'll be fun. We'll get a new table. And then when we get to chapter 12, we go back to the same old tables, just like z-tables and things like that. But next time we actually get a new table called the F distribution. And it's even more fun to read because there are 2 degrees of freedom. So anyway, we're done for today. We're just going to call it a day. We're a little ahead, so I want to kind of slow down a little bit. Maybe even take a day off next week. So yeah, any questions? If not, have a good weekend, and I'll see you on Monday.